Okay, I hope you can hear me. Okay, so I need your confirmation that you can hear me. Um, so good day, everybody. Today we are going to continue our discussion about, you know,
Darius Aprioitu said I hear you.
good, um, about performance in computer systems. That's our second chapter. So we start this new section called quantitative principles of computer design. Okay, and um, these principles are actually based on experience and a set of um, important observations made about design, computer design. So the first one is very simple. Take advantage of parallelism, right? So it's a very important principle that consciously or not, we are all taking into account. If we can parallelize stuff, then we better do it. And over the time, you've seen, at least in hardware, stuff like that. For instance, think about um, carry look ahead adders, right? I'm sure you've seen this type of design in these computer architecture classes um, and lectures. So last year or last semester rather. Um, so the thing is that um, we also have pipelining, which means instruction level parallelism, overlapping instruction execution, stuff that you will learn next semester when you'll study computer engineering fundamentals, this class. Um, Also, yeah, I mean, this is uh, pipelining is based on a key insight that allows it to work. And that is this insight is that not every instruction depends on its immediate predecessor, such that they can be parallelized. Um, so this parallel execution, complete or partial parallel execution of instructions may be possible. Um, of course, there is also, yeah, pipelining it's at instruction level. Carry look ahead adders are at a very low hardware level, but there is also system level parallelism in hardware, right? When you have multiple processors or multi-core systems. So there's a lot of stuff here in terms of parallelism, not to mention software, of course, where you can simply capitalize the inherent parallelism of several kinds of applications, such as, for instance, um, uh, ticket reservations where you have massive task level parallelism or data level parallelism, the data level parallelism represented by graphical applications, right? When you have an image and you have to process an image, you can split that image in different parts, and you can parallelize whatever you are trying to process on the image, right? So there is inherent data level parallelism when we talk about images, and inherent task level parallelism when we deal with applications where many users are doing simple things at the same time. That's why I mentioned the example with a ticket with ticket reservations. Okay, so yeah, that's a first principle. The second one um, goes like this: is the principle of locality, which is which works for humans. I mean, there's a bigger probability that you'll be friends with somebody somebody nearby than somebody who is at a long distance. I mean, it's not it's not impossible to be friends with someone who's placed, I don't know, in on another continent or something like that, but the probability is smaller nonetheless. It's the same thing here. I mean, this is based on a fundamental observation that comes from the properties of programs, which we've seen in this industry and in this scientific domain, computer science and computer engineering, over the years, right? And these fundamental observations um, show that this principle of locality is ubiquitous. And this principle can be stated as follows. Programs tend, you see, it's a probabilistic issue, to reuse data and instructions um, they have used recently. Okay, so if you are using an instruction, there's a big probability that you'll use it again. Um, Something similar goes under the name of Lindy's law, which is, to make a long story short, it goes like this. In New York, there's a cheesecake shop called Lindy's, and this coffee shop, people from New York University, physicists to be exact, met with people from the entertainment industry. You know, people who act in those musicals, which are very popular in New York, and in this industry, um, I mean, this industry is very capitalistic, to if you like. If a show does not have success, they simply drop it, right? And if a show has success, is a musical has success, then that musical will be played over and over again. And they actually observed that there's a bigger, I mean, the older the musical is still alive, the bigger probability that it will remain alive for a long time. I mean, uh, just think about it. What is old and considered as good, like Shakespeare or whatever that is not perishable, like human life, or I don't know. Right? When you think of an, I don't know, a book, a good novel, or a symphony, or whatever, if it's good, chances are that people will listen to that symphony again over the years. So this is Lindy's law. This is something similar, right? So it's connected to our lives, and um, it's a question. Ultimately, it's a question of preference. You prefer something over other stuff simply because it's good, or I don't know, because other people are choosing that stuff. But nonetheless, this is goes beyond the scope of these lectures. So let's not waste time with this, and focus on computers. So um, an implication of this locality principle is that we can predict with, I mean, reasonable accuracy what instructions and data a program will use in the near future, right? And these predictions are based on the information and the accesses and observations that we made in the recent past, right? So we've seen which instructions were used or data were used, and then we can predict that they will be used again with reasonable accuracy. Um, and there's more than that. In computer and software engineering, there's a widely held rule of thumb that goes like this. Um, a program spends 90% of its execution time um, in only 10% of the code. Again, this is not something that is unfamiliar with things where preference plays a role, and things where there is not a physical limitation, like human height or weight, right? When there's it's a physical limitation such that you cannot see a person that has 10 meters that is 10 meters tall or something like that, right? So there's a physical limitation. In other stuff, in other systems or activities, there is no such thing as a strict physical limitation. This is software. It's the problem with softwares and programs, but it's also the case with economy and money, right? There's no physical limitation on how many on how, I don't know, rich a person can be. I mean, ultimately, it can one person theoretically can have all the money in the world, but um, in economics we have that Pareto rule, 80-20, right? 20% of the people will have 80% of all the wealth in this world, and apparently there's this Pareto distribution in economics. Now, there's the same thing here in computers, right? Because we have preference with programs and software. We deal with real world problems. There's a similar distribution, similar to Pareto distribution, only that in software, in computers, the discrepancy is even bigger. I mean, we have a 90-10 percent type of rule here in computers. This rule, in principle, better applies to instructions, but it also applies to data accesses. So um, um, this locality principle is more pronounced when we are talking about instructions, but it applies to data as well. Okay, so we have two types of locality, right? Namely, temporal and spatial. Um, Temporal means that the access items, these items are obviously data or instructions. So these are items that CPU, for instance, will access, right? Wants to access. Um, so accessed items are likely to be accessed again in the near future. And of course, there's the other aspect, that the spatial aspect, which means that the items, again, data or instructions, whose addresses are near one another, right, tend to be referenced or used close together in time. Right? So if they are close together in space, they will also be close together in time. Okay, so yeah, that's the locality principle, and this, as you will see, this principle is very useful for when we design memory hierarchies. Why? Because the data and the instructions are held where? In the memory, right? So it means, according to this principle, it means that there is a locality aspect in, in memories, because we have to design memories such that we acknowledge the fact that there is a minority of instructions that are used most of the time, and most of the instructions and the data will only seldom be referenced. So yeah, it is important, right, when you design efficient memory hierarchies, uh, you have to take into account this principle of locality. And the third principle is focus on the common case. Well, this is again very powerful because it is maybe the most pervasive and important principle in computer design. This one, focus on the common case. Why? Because oftentimes you have to make trade-offs. Uh, you have to make trade-offs um, when you allocate resources, right? So you want to um, optimize something, to speed up something in your computer system, and you only have limited resources. And the question is, what part of your system will be optimized? Which one? Obviously, the answer, according to this principle, is the part that is mostly used, that is the most common in the usage of the system. Um, so yeah, but and one extra thing that comes to our help is that Oftentimes, the frequent case is the simplest one, and the case that can be implemented faster. So that is a huge advantage. So it seems that it is natural that the simplest case is the most used case, right? So that's also not uncommon in science, right? I mean, we have Occam's razor as a also as a principle, as a rule of thumb, right? Which states that when there are several explanations for something that is not clear, the most plausible one is the simplest explanation, right? So that's a general principle, right? It's a pervasive principle in real life, after all. Um, in order to to quantify this principle, people use the so-called Amdahl's law, right? Amdahl's law is used to compute the overall speed up of a system when only one part is optimized. Obviously, when one part is optimized, the whole system has to gain something, but it is a quantitative assessment of what the overall system has to gain from the speed up of uh, subpart of that system. So Amdahl's law states that this per, um, uh, performance improvement, all right, um, is to be gained um, from using some faster mode, all right, of execution. Um, that is limited by the fraction of time. Uh, the faster mode in which the faster mode can be used, right? So the only limit for the overall system is the amount of time or the fraction of time in which you actually use that speed up. Um, I mean, uh, Amdahl's law actually defines the speed up that can be gained by using a particular feature at some point. Um, to this end, I want to present you an analogy, maybe I don't know something between an analogy and a metaphor, which is presented in also presented in David Patterson and John Hennessey's book. And this analogy is goes like this: imagine that you um, I don't know you want to leave Las Vegas and um, get to Los Angeles. So right, you are here, Las Vegas. Okay, and okay, um, at, in the I mean, in this trip, you will have a fixed point of right an intermediary point at Sierra Nevada, mountains, and the distance is 80 miles. You are forced to go by foot on this segment of your trip, and then you want to go to Los Angeles. But in Sierra Nevada, you have and there are 200 miles between these two. Okay, so you have nothing to do between Las Vegas and Sierra Nevada. You have to go by foot. But when you get to Sierra Nevada, then you can, I mean, you have options. By foot, you are going, so your options are these. I'm going to put it like this. Okay. You have a vehicle for the second portion. Right? And hours for the second part of the trip. You have speed up, the speed up. For speed up for the second part. Right? When you go through the desert between Sierra Nevada and Los Angeles. Hours for the entire trip. And of course, the speed up for the entire trip. Yeah. And as I said, first you have feet. Nonetheless, for feet, I mean, your if you go by by your feet, I'm going to write it here. So the speed for feet is 4 miles an hour. For I don't know, you use a Hyundai, no, a bike first, a bike, and your speed will be 10 miles an hour. You can use a Hyundai, I don't know, low scale Hyundai. You can go with 50 miles an hour, right? You can use a Ferrari and you can go with 120 miles an hour. And you can use a rocket car through the desert and you can go with 200 miles an hour. Okay, so these are the alternatives, right? So if you go with your feet, that means that you have 20 hours, right, for the first part of the trip. But what about the second part? Now, it's clear that you have 50, right? So you divide by 4, 200 by 4 miles an hour, so you have 50 hours for the second part if you go by your feet. And the speed up in the second part is 1. I mean, there's no speed up. You cannot speed up what you already have, and that is walking. The hours for the entire trip is 50 plus 20, namely 70. And the speed up for the entire trip is 1. Again, there is no speed up, right? Now, if you use the bike, and I'm going to Hyundai, Ferrari, and rocket car, right? See what happens. Now, when you use a bike, so it's 10 miles an hour, 20 hours, obviously, for the second part. So the speed up, what is the speed up? It's 50 divided by 20, right? So it's 2.5, 2.5, right? That's the speed up. The hours for the entire trip is 40, and it's right. It's 7 divided by 4. That's the overall speed up, right? Right. So it's 175. Let's round it up to 1.8. That's the overall speed up. Okay. Now, if you go by Hyundai with 50 miles an hour, obviously there's a 4-hour trip for the second part, which means that the speed up is 50 divided by 4, which is 12.5, and you have 24 hours because it's 20 plus whatever is on this column, so it's 24 hours. You cannot change those 20 hours for the first part of the trip. So you have the speed up of 70 divided by 24, right? Which is 2.9166 or whatever. Let's take 2.9, leave it like this. Now, with the Ferrari, right? So with the Ferrari, let's see how many hours are with the Ferrari. So we have 200 miles, and we have 120 miles an hour. So it's 167, right? 167. We round it up, right, to 167 hours. So it's 21.67 overall trip. So let's see the speed up for the second part. So the speed up for the second part is 50 divided by 167. All right, so it's 29.9 or whatever. Okay, let's say 3. No, no. It's 30. No, 30. Okay. Okay. And then we have 21.67. I mean, the speed up, overall speed up is 70 divided by 21.67. So that would be 3.2, right? 3.2. That's the overall speed up. And the rocket car, I mean, it means 200 miles an hour to 100 miles, so that's an hour. Obviously, it's a 50 times speed up, 21 hours. So the so it's 70 divided by 21. So that's 3.33. So it's 3.3 speed up. So as you can see, even though we achieve important speed ups for the second part of the trip, the problem is that the overall speed up doesn't increase that much, right? So we achieve even, we are going depending on the means of locomotion. Um, you can go, I don't know, speed ups of 50 times and stuff like that. So ginormous speed ups achieved for the second part, but still the overall speed up is not that impressive, right? So in comparison, at least with the speed up for the second segment of the trip. So why is that? It's simple if you think about it. So we what we do is that we are talking about speed up of the enhanced system, and this speed up is the performance um, of task. The task is getting from Las Vegas to Los Angeles using the enhancement. But again, you can only use the enhancement for a fixed portion of the entire trip, and performance of task without enhancement, the enhancement. And this is obviously the execution time is the other way around when you put it in terms of execution time. Execution time of task without the enhancement divided by the execution time of task using the enhancement. Okay, so this is ultimately, this goes like this. So execution time, right? In terms of execution times. So it is the execution time of task without the enhancement, right? Divided by the execution time of task without the enhancement multiplied with 1 minus fraction enhanced fraction enhanced is the fraction of the task where the enhancement is possible. In our example, is the fraction of the total distance of the trip where we can use the enhancement, namely some form of locomotion, right? Plus, plus um, um, fraction enhanced like this, right? Fraction enhanced divided by the speed up enhanced. Now, I'm sure you can easily notice that if there is no enhancement, there is no fraction enhanced, this is simply is zero, so it's one. It's one. The enhancement is one, right? Right. So now this can be simplified, this fraction, so such that this is all equal with, and I'll write it here. It is 1 divided by 1 minus fraction enhanced right, plus fraction enhanced divided by speed up enhanced. Speed up enhanced is the speed up for the second part of the trip. Right? So you can see that right, this is the speed up enhanced. If we when I use the same notation, it's not speed up. How should I call this? Speed up overall. Overall, yeah, I made a mess out of this. Speed up overall. So when speed up overall is computed for a speed up enhanced that goes to infinity, right? So imagine that for the second trip you'll take, I don't know, the speed of light or something bigger than the speed of light. So it's infinity, right? This would be 1 divided by 1 minus fraction enhanced. And that is the limit of our speed up, overall speed up. In our case is 1 minus 1 divided by 1 minus, so what is the fraction enhanced? The fraction enhanced is, in our case, so this quantity, right, this one, yeah, is, I'm going to compute it here, in our case, so it's 200 miles out of the 280 miles of the total trip. So is, right, 20 divided by 8. So it's 0.71. Yeah, 71. So this is 1 divided by 0.29. Right, so right, it's 344. So you see, there's a limit there's a limit, a fundamental limit for whatever you are trying to speed up. When you enhance only a part of, of, of the system, right? Overall, there's an enhancement, but nonetheless, this enhancement is limited by the time you can use the actual enhancement. Okay. Good. So let's move to our new section, which is called 2.5, the processor performance equation. Good. Now, essentially, all computers, you know, this are modern computers. Obviously, there were a lot of attempts to build different type of computers, different from what I'm going to say, which is the norm right now in building computers. But essentially, all computers are constructed, you know, using a clock, right? A clock. So it's a synchronous device, our computer. So you have a clock that runs at a constant rate, right? So that's a fact. And these discrete time events are called ticks, clock cycles, or clocks, simply clocks. We'll call them clock cycles. Everything that a computer does in terms, when you measure time, this time is in terms of clock cycles. So it's an integer number of clock cycles. You cannot have, I mean, when somebody puts you and asks for I don't know, how much time does it take to run, I don't know, some program, and the time that you report has to be a multiple of, you know, periods of that clock cycle times, of the clock cycle time. So you have n times, I don't know, the clock cycle time. You cannot have, you know, 2.5 clock cycle times or something like that, unless we are talking about some average, right? But in absolute terms, we are talking about clock cycles. So when your program runs, it runs in a given number of clock cycles, and that's very, very important. Of course, sometimes you are not, you know, thinking about clock cycles in terms of clock cycle time, but you are also uh, talking about, maybe talk about a clock rate, right? Which is obviously 1 divided by the clock cycle time. Okay, and therefore, when we are talking about CPU time, right? Because we already discussed that this is the most important and the most accurate way of characterizing computer performance, um, using the CPU time. And so the CPU time is the clock, CPU clock cycles for a program times the clock cycle time, right? So you simply multiply the number of clocks required by running your program with the clock cycle time, and there you have it. You have the CPU time for your program. And of course, it can be CPU clock cycle times for a program divided by the clock rate, but I'm not going to write it because it's obvious. Now, yeah, that's a good equation, but nonetheless, it's not that easy to simply count on the number of clock cycles and assess the number of clock cycles that a program will require. So we need to be more specific and to divide this CPU clock cycles for a program into different, to break it down in different parameters. To this end, we will use what we call instruction count. This is something that we can measure very accurately, and that is the number of instructions required by running a program. Right? When your compiler compiles a program, you know for sure what is the exact number of um, assembly language instructions that you need to run. Right? I mean, involved by this program. And this instruction count is to be multiplied with the clock cycles per instruction. And this is an average, clock cycles per instruction. And of course, these two, right, these two are making the clock cycles for a program, right? They give the clock cycles for a program. And therefore, we just need to multiply this with the clock cycle time. Okay? So in short, we are writing this as IC, instruction count, times CPI, clock cycles per instruction, times the clock cycle time. Good. Now, CPI, the CPI is an average, and of course is the CPU clock cycles for a program divided by the instruction count, or in short, IC. Okay. This is not circular at all, because actually we can estimate the CPI from catalogs where or maybe from experiments where you can break it down. CPI, you can reconstruct the overall CPI from the CPI of each type of instructions, assembly language instructions. You know that in assembly language, you have arithmetic logic instructions, compare instructions, I don't know, logical instructions, arithmetic instructions. Maybe I said arithmetic again. Load store, branch instructions. So you have several categories of instructions, and you can calculate the CPI for all of them. And then you only need to know what is the mix of instructions, namely how many, or in other words, what percentage of instructions in our program are represented by branches, and so on and so forth, right? So yeah, um, to verify what we are seeing here and that we are measuring things, the correct things, um, um, let's think of this equation, computer performance equation, in terms of what do we measure. I mean, with the instruction count, we measure the instructions per program, right? Whereas the CPI, with the CPI, we measure the clock cycles per instruction, And with the clock cycle time, we measure the seconds per clock cycle. So when you simplify this, right, what you get is seconds per program. And of course, this is what the CPU time measures. The CPU time is equally dependent on all these characteristics or parameters, namely IC, CPI, and clock cycle time. So the CPU is equally dependent on all these three parameters. Moreover, because these parameters are multiplied, it means that, I don't know, a 10% improvement in any of these parameters leads to a 10% improvement overall. So it's very easy to quantify whatever, theoretically at least, whatever type of improvement you bring to the system, because a 10% improvement for one parameter, it means a 10% overall improvement. Unfortunately, it is very, very difficult to change just one parameter because they depend on each other. And that is the key observation that led to David Patterson and John Hennessy coming up with the solution of a RISC processor and a RISC architecture for, and of course we know right now that this is the uh, you know for general systems is the best idea. You can achieve better performance, mainly due to the fact that when you have simpler instructions, because that's the idea. That was their idea. In short, their idea was this. I mean, look at this equation, right? And what do you think that the designers did traditionally before Patterson and Hennessy? They said, okay, we need to improve our system. What do we do? Well, the most available thing to do is to try to minimize the IC, namely to minimize the number of instructions. So of course, if you minimize the number of instructions, you get an overall performance. But how do you do this? Well, you try to build computers with very strong instruction sets. To give you one example, instead of adding just an addition with I add two operands and I put the result in a register. I add three operands and put the result in a register, right? Or I can go far further and add four, I don't know, operands and put the result in a register. So in other words, to make stronger individual instructions. One instruction can do a lot. The problem is that if you have such very strong instructions, you cannot parallelize them. Remember, we discussed about instruction level parallelism, the fact that the instructions can be parallelized because they consist of different stages. For instance, we have at ARM, we have three stages. Maybe I showed this in the past view. So I'm not going to delve into details what this each and every stage mean, but you have a different execution. You'll learn all of it, and I'm not going to spoil this to you, in computer engineering fundamentals. So you can parallelize like this because you have a different execution unit for each of these stages. So you have 1, 2, 3. That's for ARM, for the ARM processor. right? And for the next instruction, yeah, 1, 2, 3. But ARM is a RISC type of architecture. It contains simpler instructions. When you have more complicated instructions, you will have more than 3 stages. Now you see in just 1, 2, 3, 4, 5 clock cycles, we execute 3 instructions, whereas in the case of non-pipeline, that would have required 3 times 3, 9 clock cycles instead of 5. So you see, that's how through pipelining you achieve performance. But if you have more complicated instructions, you will have more, you will be forced as a computer architect to build hardware to support more than 3 stages. And when you have more than 3 stages and you have many stages, right, it becomes more and more complicated to parallelize instructions. So what is the result of all of this? The result of all of this is that, okay, you improve the IC, but you actually you degrade the CPI. You degrade the number of clock cycles per instruction. So what you win in terms of instruction, on one hand, you lose it on the other hand, and sometimes you lose bigger than you win. Okay, so that's a acute observation from David Patterson and John Hennessy. But at this moment, what you need to bear in your mind is that these 3 parameters are are connected. They cannot be simply manipulated in complete isolation from each other. So the the aspects involved here for each of them are the following. Well, when we talk about the clock cycle time, we are talking about hardware, technology, and organization. Technology, hardware technology, and computer organization, right? Um, when we are talking about CPI, we are talking about computer organization and instruction set architecture. These aspects are influencing these parameters, right? Whereas the instruction count is influenced by what? Is influenced by the instruction set architecture and the compiler technology. Good. Good. So let's focus right now. Let's focus on you know um, computing the CPI from those fractions of, if we know the individual or the CPI for particular categories of instructions, things that we already discussed about. So it all starts from this equation. Oh my God. right? So if we have a number of n categories of instructions, for each category we have an IC, namely a number of instructions from that category. So ICI is the number of instructions of category from category I. CPI is the clock cycles per instruction for category I. Category can be, I don't know, arithmetic instructions, for instance, or I don't know, branch instructions. Okay, so yeah, ICI is the number of times instruction I or category I is executed in a program. Ultimately, of course, each instruction can be in its own category, so you can, estimate the CPI for each and every instruction, particular instruction, and you can, you know, um, count each and every instruction. And CPI is the average number of clock cycles or clocks per instruction for instruction I. Okay, yeah, so then the CPU time, or rather the CPI, right? The CPI will be this sum where, of course, IC is the sum of all individual CPIs, ICs, sorry, right? And therefore, the CPI will be the sum so CPII, we already defined this, and this is the fraction, right? This is the fraction of occurrences of instruction type or category I in the program. Okay, so the CPI should be measured normally when you want to really assess the performance of a computer system. It's better to, I mean, it's best to just compute it and not take it from a table or a reference manual or something like that. Where because if you take it from a manual, most of the times those figures will not include, I don't know, the effects of the pipeline, the cache misses, things that we will going to discuss in the future weeks, in the weeks to come. So you need to, if you want to be accurate, just measure it in an experimental manner. Okay, so let's take, at this point, let's take an example. Example one. And see how all these things are working. So the example is taken from Patterson and Hennessy. Okay, so it's a problem that is put at the end of the chapter, and it goes like this. So suppose that we have made the following measurements on a computer system. Measured for running when we run a particular workload, right? So we run a workload on this computer system. This workload can be very well can be a benchmark suit such that the, this assessment is also predictive for any type of program, as we saw in our previous lecture. So now, so we make measurements on this computer system, and we measure these parameters. The frequency of floating point operations or instructions is 25%, right? So 25% are floating point arithmetic operations. The average CPI of floating point instructions or operations rather is 4.0. Nice number. It can be also a fractional number, right? Because it's an average, right? So it can have something to the right of this point. Normally, at this point, I should ask students a question. What is the minimal CPI for any instruction? But the minimal theoretical CPI for any instruction, but right now it's hard for us to communicate and to have a feedback. So I'll go right ahead and tell you that it has to be bigger than 1. Why? Because I mean, you have to have at least 1 cycle to execute the instruction, right? So it cannot be something smaller than 1. Okay, but we will talk about these things and other things in the weeks to come. Right now, let's focus on this. So it's 4.0. The average CPI. This text is taken from Patterson and Hennessy, and it's kind of redundant. Average CPI. The CPI is by definition an average, but let's go by the original text. So the average CPI of other instructions is 1.33. The frequency of a particular floating point operation, namely floating point square root, is 2%. Okay. The CPI of floating point SQRT, right? This particular instruction is 20. These are clock cycles, right? Clock cycles, right? And given these facts, we assume, right, that rather these measurements, that there are 2 design alternatives. One is A, alternative A, decrease. I mean, imagine that the hardware guys, the hardware designers, you ask them, people, guys, let's optimize this design, this processor design, and these guys, maybe you have two teams or just one team that presents two alternatives, and they say, okay, we have this, we can do this thing, this alternative, which will result in a decrease of the CPI of this floating point SQRT instruction to which is a huge, right? Is a huge 10 times, right? Speed up. From 20, you go to 2 clock cycles per this instruction. Or alternative B, these guys are saying, okay, we have another alternative, which will result in the decrease of the CPI in all floating point instructions. 2.5. It was 4, and now it will be 2.5. It's not such a big overall. It's not such a big speed up, but let's see what happens here. Which alternative is the best? So you are the team leader, okay, and you assess the performance, and you'll tell them which alternative to adopt ultimately. So let's see about the answer. First of all, prior to getting to alternatives A and B, you are starting from the original machine. So you have an original machine, right? And the CPU time of the original machine is IC, original, instruction count, original, times CPI, original, times clock cycle time, original. Now, let's stop for a second and think about it. Now, for both alternatives, whether we are talking about alternative A or B, we do not change the clock cycle time, right? So the clock cycle time will remain the same. And it's the same thing for the instruction count, right? We do not change the instruction count, which is, we simply, I don't know, make something in the computer organization at a hardware level, such that the number of, because the compiler is the same, the number of instruction will be the same. I mean, the instruction set is the same. So the number, the IC, which is only influenced by the compiler or the instruction set, will remain the same, right, for both alternatives. Also, we do not change the, I mean, the problem doesn't, the exercise, the example does not say that, um, you know, that the clock cycle time is changed. So we assume that it is unchanged. The only thing that changes here for both alternatives with respect to the original machine is the CPI. Now, so if we compare, because the other parameters remain the same, right? The same. The only thing that makes a difference between the performance of these machines is the CPI. So these remain the same. Right? So let's compute the CPI original. CPI original is very simple to compute because it's 25%, namely 0.25. These are floating point operations, and they require 4 clock cycles, so it's times 4 clock cycles plus all the other instructions, 0.75, so 75%, all the other instructions, times 1.33. Now, let's do the computation. So it's 1, 4 times 25, but 0.75 times 1.33 plus 1. Well, let's round it up to 2. So it's 2 clock cycles. Okay, and then let's see what it means for CPI for alternative A. For alternative A, we have something like this. I mean, we have the CPI original. It is the same thing, but only one type of instruction. Actually, one instruction changes in implementation, namely the f floating point square root, right? But that happens only in 2% of the cases. So I'll subtract the number of clock cycles on average, which are eliminated by the fact that we've made this enhancement, this optimization. I mean, the hardware team has made this optimization such that we will have here, what do we have here? What do we subtract? Well, the CPI old, the old CPI for, this is the CPI FPSQR old minus the CPI F floating point SQRT new. The difference, namely 18, is the number of clocks on average that are won or eliminated for each such floating point square root instruction. But this elimination of 18 clocks works only for 2% of the total. Why? Because only 2%, they represent only 2% out of all instructions. So this is CPI original, which is 2 minus 0.02 times 18, and this is this will be 36, so 0.36, so it's 1.60 clock cycles, of course. Right? Okay. Now, let's see for alternative B. For alternative B, it's simpler because we have the percentages. I mean, what we change is the CPI for all these floating point instructions. So we also have 0.75 times 1.33, right? These are all the other instructions, plus 0.25. These are the instructions that are speed up by the enhancement entailed by alternative B. So the CPI, the new CPI, instead of 4 will be 2.5. So so this is actually almost 1. It's approximately 1. We've seen this in the other uh, um, equation or yeah computation that we've made. So we have 0.25 times 2.5, and this is 0.625. So plus 1, this will be 1.625 clock cycle. Now, obviously, the most performant machine is the one with a smaller CPU time. And the CPU time is goes the same way as the CPI, right? If CPI is bigger, then CPU time is bigger, therefore the performance is smaller. So, which is the most performant alternative? Alternative A or alternative B? Obviously, the best alternative is this one, right? Alternative um, B in comparison with both the original machine. Of course, with the original, it's better because we've optimized something without losing anything else, but it's better than alternative A as well. And this example is not taken just by chance or proposed by chance by Patterson and Hennessy, because it has a deeper meaning, and the deeper meaning is very much related to what we already discussed, namely Amdahl's law, right? So you see an example of Amdahl's law at work. In other words, you see that sometimes it's better to come up with smaller um, mm, um, speed up, but that speed up, when that speed up is used more frequently, right? Because uh, the speed up is, I don't know, it's smaller than 2, right? For alternative B. For alternative A, the speed up is 20 times, right? So 20 times is obviously better than 2, or something that is smaller than 2. But the thing is that the speed up from alternative B is used more frequently than the speed up entailed by alternative A, and that's key, right? It's key that your improvement be used, more frequently. Okay, good. So I don't know if we have more time. We have some more time. We will take an example. Two. Maybe we'll have at least the time to write down you know, the text of this example. So in this example, we also analyze 2 implementation alternatives. And these alternatives involve the usage of conditional branches. All right, 2 alternatives for computer systems. Right. So we are talking about conditional branches. And on one hand, we have machine A, which has CPU A, that's alternative A, corresponding to alternative A, which has a conditional code set by a compare instruction, right? After which the subsequent instruction is tested, is testing the condition code, and therefore the conditional branch will decide if the branch is taken or not. In other words, let's take let me translate this to you. So if you have something like if I don't know, x equals y, then something like this. I'll write this in some pseudocode or something. Then I don't know, jump to address, right? Now, how does CPU A is going to deal with this? Well, simple. It will do something like this. Compare. We assume that X is in register R1 and Y is in register R2, right? So it will compare R1 and R2, and then we will have jump if equal, right, to address. I mean, if R1, namely X and Y, are equal, and I test this with the compare instruction, then I jump if they are equal. Then yeah, it will jump to that address. Now we have also a CPU B, which deals with the same problem of conditional branches this way. It is including the compare in the instruction. In other words, we suppose that we have something like this. Jump if equal R1, R2, address. Okay, so instead of two instructions, we execute one instruction. Okay, good. So we have these two alternatives. Now, we also assume that for machine A at CPU A, we have something like this. 20% of all instructions are branch instructions. And of course, it comes as a consequence that other 20% from the number of instructions are compare instructions. Simply because before each and every jump instruction, there is a compare instruction, right? That's why if I have 20% branches, then I have 20% an extra 20% compare instructions, because they are entailed by the conditional. We have to to test the condition. We admit that the branch instruction requires 2 clock cycles. So branch CPI branch is 2 clock cycles. All right. And all the other instructions, CPI others, for all other instructions, the CPI is just 1 clock cycle. Okay? And we neglect all the losses generated by the memory system inefficiency. We will not do the same thing after we discuss about caches, but that's another story. Now, at machine B, by introducing the compares within the branch instructions, the duration of clock cycles for machine B has to be extended. So we admit that the clock cycle time for machine B has to be extended, therefore is 25% bigger than A, right? We are admitting hypothetically that all the other organization aspects of the two systems are neglected, which means that we consider that all the other aspects and all the other, subsystems are considered as being the same. So the only thing, these two machines are the same, except what we emphasized as being different between the two machines. Are identical. Now, the solution, of course, next week. But at least we took the time to write it down, to write the problem down. Maybe if you want to try to solve it by yourselves, just maybe I don't know if I don't think it's solved in Patterson and Hennessy's book. It's only formulated there, and I think there's also a book with all the solutions of the problems, but I don't think it contains the solutions from all the editions of the book, because we are talking about, I don't know, 7 editions of the book, right? So I don't know about this, but nonetheless, if you find the solution somewhere, I'm okay with it. But nonetheless, we will discuss the solution next week. So let's hear each other on and let's go on Discord and discuss. If you have questions, I want to have at least some feedback with you, and see if there are things that I can clarify for you or something like that. So let's go on Discord. I'll stop the streaming, and of course I'll put the table, the board captures as PDF files on Discord as well. So okay, I'll end this stream, and let's hear each other on